Firstly, we are going to introduce how the high-level architecture enablers have been instantiated in the Inspire 5G Plaza infrastructure through Kubernetes, where each entity is represented by a pod. We can find two types of domains: the single end-to-end security management domain that is present in the CTTC domain, and the end security management domain that are present in all those domains that have participated in the demo, which are Telefónica, University of Murcia, CTTC, Montimatch, Everscom, and Thales. The end-to-end security management domain is in charge of coordinating the different end security management domains, while end security management domains will adapt the policy recipe from the end-to-end security management domain to its own infrastructure. So far, we have shown the two security management domains present at CTTC and the end security management domains present at Telefónica and University of Murcia, which are the three domains that will be present during the enforcement and reaction of the first SSLA. We have enabled Kiali, an observability console for Istio, which allows the graphical visualization of the Kubernetes objects, including the deployment, the pods, or even a service mesh graph where we can observe how the enablers are composed of services interconnected. Now we are going to show the initial status of the infrastructure. These are the OSM present in the three security management domains. And as you can observe, right now there isn't anything instantiated on them. This is the Microsoft GNodeB, which can't connect to the core due that it hasn't been instantiated yet. Also, it hasn't got connectivity to the I2NSF agent, which will be in charge of connecting the user and control plane of the 5G network between the RAN and the 5G core. If we access the command line interface of the GNodeB, we can check the status of the MG interface connections. And as can be seen, the connection is not established. Also, if we access the Microsoft Sandbox, which is a real radio stack for user equipment with 5G capabilities, we see that the users are powered off and there is no connection to any endpoint using them. Now we proceed with the enforcement of the SSLA among the system. The entry point of the demo is the end-to-end slice manager, which will receive an NST that describes the end-to-end 5G slice that must be deployed and an SSLA ID that corresponds to the 5G service that is going to be deployed as part of this end-to-end slice. The end-to-end slice manager then performs the following process. First, receive the information mentioned previously, which is the NST and the SSLA ID. Then retrieves their SSLA information from the SSLA manager and starts the deployment of the end-to-end 5G security slice. The MSPLOP is the policy language used by the system and it is based on security capabilities. So the end-to-end slice manager performs an identification of security capabilities based on the SSLA information. With this information, match the capabilities extracted from the SSLA with the capabilities available in each domain. Then the end-to-end slice manager constructs the MSPLOP and sends it to the end-to-end security orchestrator. At this moment, we are going to show the logs produced by the orchestration process at the end-to-end security orchestrator. The MSPLOP result is printed on the log, where we can identify the slice ID and the tenant ID that will be shared by the policies related to this specific slice. The slice-related MSPLOP is composed of a service, that in this case is a 5G core, which must be deployed at the Telefonica domain, and several MSPLs that refers to the security capabilities that must be enforced in order to fulfill the SSLA requirements. For this SSLA, the security capabilities are channel protection between the user requirement and the 5G core, which presents a dependency on the instantiation of the 5G core, proof of transit that performs a security analysis corroborating that the channel protection is working as expected, network traffic analysis that monitors the behavior of the 5G core and will be only deployed at Telefonica domain. And finally, the DOS attack protection that monitors the 5G service that in this case is a V2X service already deployed at CTTC domain. As we can perceive, the OSM shows the process of the instantiation in each domain, wherein Telefonica has already finished and right now is working on the YUMO OSM. Returning to the logs of the end-to-end security orchestrator, the MSPLOP represents an end-to-end security slice. In order to deploy the end-to-end security slice, the end-to-end security orchestrator generates the enforcement plan, deriving in which domain each capability should be deployed. Then construct one MSPLOP per domain. Each MSPLOP will only include the MSPLs that belong to the domain. As we can observe, it has been constructed one MSPLOP for each domain, gathering there the MSPLs that were required to be enforced in. For instance, the MSPL corresponding to the Telefonica domain contains the 5G core, plus the channel protection, plus the monitoring of the channel protection, plus the monitoring of the 5G core. Once the construction of the MSPLOP has finished, they are sorted by priority in two ways. The first one to dictate which domain should enforce its MSPLOP first, and the second one inside each MSPLOP in which order the MSPL should be enforced. Thereafter, we have in view the Telefonica domain's security orchestrator logs, and we are going to explain the enforcement process and the final MSPLOP is received until the service and security assets are instantiated and configured. We can see how the slice antenna identifier have been propagated to the domain. This MSPLOP is exactly the same as the one constructed by the end-to-end security orchestrator. Thus, to this MSPLOP belongs the 5G core, the channel protection, the monitoring of the channel protection, and the monitoring of the 5G core. The security orchestrator identifies the candidates for enforcing each of the capabilities, where OSM will be selected for deploying them. For the selection among the candidates, the trust-based orchestration is used, supported by the Trust Reputation Manager, which will select the NST that covers all the security requirements available at the OSM that has the highest trust. When the NST with the different asset has been selected, there is a verification of responsibility, where it is verified that the selected asset can be enforced. With the selection of the asset, the enforcement plan can be created, and it is composed of the template ID, the matching between the MSPL and the addressed asset, and the driver that must be used in order to enforce the configuration of the asset. The policy framework is now requested to perform the translation process, where the MSPLOP will be translated into the final selected asset configuration. For doing this, it will use asset-specific translation plugin. In particular, the 5G core will be translated into a free 5GC deployment, the channel protection into the I2NSF agent, the proof of transit into the pod, and the behavioral monitoring into the STA, which is a specific enabler capable of detecting cryptomanion activity. The enforced operation is sent to the OSM, which starts the instantiation. When it has finished, some critical information is retrieved, for example the endpoint IP, and the status of the policy is changed to enforce it. This is done at the policy repository. This next step shows how the final configuration is enforced on the STA. This process is specific as driver assisted, which drives the communication with the VNFs to enforce the configuration. And if the operation ended properly, the VNFs indicates the successful to the security orchestrator. As the following steps are about the functionality of the deployment made on University of Murcia and Telefonica, we are going to show the security orchestrator of the University of Murcia and briefly explain the enforcement procedure, which is analogous to the one made in Telefonica. The MSPLOP received by this orchestrator is practically the same. But in this case, this MSPLOP contains channel protection and monitoring of the channel protection. The rest of the process is analogous until the enforcement of the configurations. The enforcement of the configuration is different in this domain, due that the security orchestrator will communicate with the I2NSF and pod controller to enforce the configuration of the agents present in Telefonica and YuMu domains. When the controller has successfully configured the agents, return the status of both. Now, if we reload the OSMs from OMO and CTTC, both have finished. Thus, the whole end-to-end security network slice is deployed. And if we return now to the logs of the end-to-end slice manager, the end-to-end security orchestrator has informed back to the end-to-end slice manager, and this checks the received information and updates the corresponding NSI object with the instantiated status. Finally, the customer is informed about the correct deployment. Here and after, we are going to explain from the inside of the I2NSF and pod agents how they are configured. The first thing that appears on the terminal is the I2NSF controller, the asset that will configure the agents specified in the configuration sent by the security orchestrator. The first screen are the logs of the both agents in both domains, Telefonica and University of Murcia, when they don't have any policy applied yet. When the controller receives the configuration, it is enforced in the pod and I2NSF agent. If we check, we can notice that the policies have been applied. Now, if we check connectivity, we can see IPsec traffic between both domains. Thus, the IPsec tunneling has been deployed and configured properly. The next part is to open the instantiated 5G core and show all the main entities of the 5G core architecture that form part of a Docker deployment based on FreeFileDC software. Now, if we try to connect to the G-Node-B, the traffic will be directed by the IPsec tunnel and arrives to the endpoint. We are going to enable the logs of the AMF, thus we will see the registration of a real user equipment using a 5G multi-domain network. We can already see in the AMF logs that the NG connection has been established. If we return to the command line interface of the G-Node-B, we remember that the NG connection was on connecting status. If we refresh, we will notice that the NG connection with the AMF is done, as the PLMN of the network is 00102. Of course, if we test the connectivity in the other direction, it's performed successfully, as well as the connectivity to the YuMu I2NSF agent. At this moment, we proceed to power on a 5G user equipment that uses the Microsoft Symbol radio stack. This user will use the G-Node-B to connect to the 5G core through the IPsec tunnel, which will have connectivity to Internet and to the internal services deployed on the private 5G network. If we go back to the AMF, we can clearly see the initial registration procedure triggered with all the standardized information required to perform this operation, until the registration procedure has been completed. Finally, we will use the user requirement to show the connectivity to the data network. In order to prove that it is using the radio link, we show the web user interface of the G-Node-B to see how the GTP tunnel is being encapsulated and sent by the G-Node-B. Also, we show the same web user interface for the user equipment, where we clearly see that the ping is being sent. Now, to prove that it is using the IPsec tunnel, we go to the I2NSF agent and start capturing the IPsec traffic, and restart the ping to the data network. So, we observe that we are capturing this traffic. Also, in the command line interface of the G-Node-B, we notice that there is a user requirement with certain identifiers connected to the radio bearer. Finally, we show the connectivity of the user requirement to Internet. To finalize the practice part, we show the CTTC security orchestrator and briefly how it configures the DDoS detector. The orchestration procedure is analogous to the one shown in TID or YuMu, but in this case we are going to enforce a DDoS attack protection. After the instantiation via OSM, the V2X DDoS asset is configured. We have in view how the V2X DDoS detector is configured on the left panel and start the data gathering on the right panel. We have shown the proactive part of the demo, where the security assets have been instantiated in different domains. Now we are going to proceed with the reaction of the framework against different attacks. The first one is cryptomining activity produced inside an entity of the 5G core, more precisely inside the AMF. First, we are showing the different entities of the 5G core deployed in Telefonica domain. Also, we are showing the status of the security agent deployed as a service in the same machine. This security agent will be in charge of enforcing the security policies in the core. Now, you can see a different 5G core present in University of Murcia domain, which is part of the managed infrastructure of the Inspire 5G Plus project, but it is not used for offering services but as a backup 5G core. This core presents the same entities and version of Telefonica 5G core, but in this case, we execute the security agent manually, enabling full logs, easing the visualization of the end-to-end reaction. Now we are prepared to start the attack. On the left panel, a script is prepared inside the vulnerable AMF, which will start producing cryptomining traffic. On the right panel, we will observe how the integration fabric receives the alert, where via subscription, the decision engine will receive this alert and trigger the reactive closed loop. As you can see, the alert is forwarded to the decision engine as scriptor countermeasure. Once the reaction has been triggered locally and the mitigation has been enforced, the STA stopped sending alerts to the integration fabric. As it is shown, the decision engine receives the alert and generates two parallel processes. The first one that is in the local mitigation to Telefonica Security Orchestrator, and the second one that is the end-to-end reaction where the end-to-end decision engine will locate the other vulnerable 5G core and perform a security operation on the AMF. What we are observing now is how the 5G core security agent at the Telefonica domain have received the mitigation security policy. While this mitigation is being enforced, we show the full logs that we enabled at the UMU domain, which form part of the reactive end-to-end procedure. We can notice that the mitigation action is to redeploy the vulnerable AMF with a trustable version. Within this process, the MAF redeployment procedure is initiated in the 5G core, and the new AMFs are registered in the 5G RAN. If we check the 5G core entities, we can observe how the AMF has been stopped and there is a new AMF among the infrastructure. Returning to Telefonica domain, where the local reaction has been enforced, we can detect how the security agent has triggered the registration of the AMF in the RAN. And as well as in the UMU domain, the vulnerable AMF has been reinstantiated with a new trustable version. If we return now to the 5G RAN, we can see how the old AMF is disconnected. The UMU AMF is in connecting status as it is defined as a backup core, but it is not yet enabled in the RAN, and the new TID AMF has been connected and it is operational. To show that the 5G network is still functional, we access to the Microsoft Sandbox and connect a user equipment to the network, which for registering will use the only operational AMF present in Telefonica. We can see that the user keeps connectivity to internet. Now we are going to show the logs from the HLA enablers that drive the reactive closed loop. The last step we introduce is when the decision engine triggers the two reactive processes. Firstly, we focus on the local mitigation closed loop, where the loss of the Telefonica Security Orchestrator show the enforcement of the AMF redeployment. For this, it receives an MSPL OP, which specifies that the capability to be enforced is a secure service manual, which targets the AMF of the free 5GC instantiation, and the operation is to redeploy. The enforcement process is performed as usual. A conflict detection procedure is triggered, which returns as successful. As the security service manual, the only possibility is the 5G core security agent. Then the enforcement plan is created, which focuses on the configuration of the 5G core security agent. For this configuration, the security orchestrator uses the data services to retrieve the entry point of the security agent. and then it will use the Docker agent plugin for translating the received MSPL OP into a JSON configuration for the 5G core security agent. After the local mitigation, we are now focused on the end-to-end reaction, where the end-to-end decision engine have received the crypto alert forwarded by the Telefónica decision engine and communicate with the end-to-end security orchestrator to enforce required mitigation security policy among the system. The end-to-end security orchestrator receives the MSPL OP, which contains similar information as the one generated locally in Telefónica, but the domain points to University of Murcia. Particularly, it will target the other 5G core present in the system that also present a vulnerable version of the AMF. The end-to-end enforcement procedure is analogous to the one explained in the proactive part. The end-to-end security orchestrator creates the enforcement plan and forwards the created MSPL OP to the UMU security management domain, where the security orchestrator will perform an analogous procedure to enforce the MSPL OP on the 5G core security agent. As you can observe, the MSPL OP is practically the same that the one received in Telefónica Security Orchestrator, but the domain is different. Also, it will use the Docker agent plugin to perform the translation between the MSPL OP and the final asset configuration. That will eventually enforce the configuration of the redeployment of the AMF through the specific drivers. For this part of the demo, we show that the GNodeB have two self-defined, with cell ID 1 and 2, where one of the cells has the peculiarity that has the uplink disabled, so any user connected to it won't be able to communicate with any endpoint. We have two user equipment connected to the network, as we can observe on the right panel, with IP 6060.01 and 6060.02. Now we start producing genuine V2X traffic through one of the user equipments. We can observe the GNB logs that this traffic is being sent through the 5G radio link. If we access to the logs of the Symbox, we notice that the user equipment is sending data. At this moment, we are starting the DDoS attack through the other user. Once the attack starts, the aggregated information constitutes a time series repository of the received basic safety messages. Then, a DDoS detection takes place sequentially for a number of training episodes. The key performance indicators pertain to the DDoS detection assessment are calculated: mean time to detect, false positive rate, and false negative rate. Next, the decision engine provides the verdict to the security orchestrator to apply the predetermined reactive security policy. The DDoS messages originated from the malicious IP address to be filtered. The policy is being sent to the security orchestrator, and the security orchestrator enforces the reconfiguration of the network filtering asset. The JSON file shown in the left screen contains the configuration directives to be enforced in the filtering asset. We are accessing now to the UMU security orchestrator to watch the end-to-end reaction triggered by the detection of the DDoS attack. The security capability of the policy is filtering with the deny action on certain IP, which corresponds with the user equipment that is performing the DDoS attack. The enforcement procedure continues as follows: conflict detection procedure, asset selection via trust-based orchestration, creation of the enforcement plan, we select a Microsoft as the asset to configure, and policy translation, which for this case it is translated into a run agent configuration, which will have to retrieve the radio link identifier related to a specific IP. Returning to the GNodeB, we can see that there is only one link connection active. Checking now the web user interface of the user equipment, we can observe the message sent by the RAN to reconfigure the user equipment to use a different cell. Watching now the right panel, we notice that the specific user command is sending the rats trying to reconnect to the network. Firstly, we are going to show that there is no slice for IoT channel at the beginning. Now we initialize a new slice for IoT. Now we confirm the new slice via OSM command line. The TTLS proxy is deployed by default on the Kubernetes master node. We confirm the new slice via open source manual graphical user interface. We have in view the network traffic of a DTLS proxy on the Monty-Match Security Analysis Framework graphical user interface. As an attacker, we modify the cipher script of the DTLS proxy. Immediately, the Monty-Match Security Analytics Framework detects this attack. It notifies the decision engine. The decision engine takes a decision to require the security orchestrator to deploy the DTLS proxy on a safe location. We confirm that the new deployment was done on a safe work node. The IoT channel downs during the mitigation, about 30 seconds. Then it works normally.